Okay, so we have talked about the evaluation designs and all of that. We talked about RBM, we talked about LFA, we talked about theory of change, right? So let's assume that we finalize the evaluation design. The next step would be to finalize the sample size or the sampling, right? So the sampling strategy is the next step that we need to finalize. So we are at 3:16 p.m. I'll try and cover everything in the next one and a half hours, and then we'll wrap up the session for today. Okay, so sampling, we realized that sample size, it's better to go ahead with the sample survey rather than going ahead with the population survey. Population survey would mean interviewing every member in the sampling plate, right? So in this population, this is the sample, right? And the reason why we have put that in different colors is to ensure that we have a true representation. We have all of these people represented in the sample that we've taken. The more representative the sample is, the better we'll be able to generalize our findings later, right? So a good sample should definitely be a true representation of the entire population. The sample characteristics, nobody is interested in the sample characteristics at all. So the sample should give information about the population. So that is basically inferential statistics that we have talked about yesterday and today also, right? So a few things that I just wanted to point out. No matter what you do, at the end of the day, once you have drawn a sample from the population, no matter how much effort you put in, it might not be the best, representation of the entire population. It will still be closer to the best possible representation, but not an exact representation. An exact representation of the population would be the population itself, right? So the difference between the kind of representation that is possible in a sample vis-a-vis the true representation in the population is called sampling error. Say in this class, let's say there are 20 people sitting here. Out of 20 people, I don't want to go ahead with a population survey interviewing all of us. I draw a sample of 5 people, right? But that's the kind of response that I get might give me an estimate of, let's say 60%. 60% are liking this class, okay? But had I interviewed all the 20 members, that percentage might have fallen to 50%. So there is a 10% difference. Now that 10% difference is basically happening because I have failed to interview all the members in this class, right? So there will always be a difference. So that difference is basically called sampling error, right? There are other kinds of errors also that creep into the data collection process. So if you start collecting data, and for certain indicators you haven't been able to collect the data at all, you've missed collecting data for certain indicators. Missing data is something that is non-sampling error. So the reason why we are making this distinction here is to understand what can be rectified at the sampling stage and what cannot be rectified at the sampling stage. Okay, so if you're missing the information while collecting the data, that is something that we call a data collection error. Okay, recording. So if you are not recording certain numbers, certain indicator values, that is not a sampling error. That is not something that you can address at the sampling stage. Data entry error. Maybe I've requested you to share your age with me. You mentioned 35. I've mentioned 53. Okay, so that is a data entry error. That is not a sampling error. Analysis error. You were supposed to put a few things in the denominator. Instead, you put them in the numerator. Obviously, the value that you get at the end of the analysis is wrong. So that is not a sampling error, right? Poorly conceived concepts, unclear definitions, and defective questionnaires. Like the one that we talked about yesterday, if I'm supposed to understand what has been your household income, I can't simply ask you in one question, what is your household income? Because I'll have to administer at least like 10, 15, 20 questions to get to the right or the correct response, right? Response errors, error occurs when people do not know, sorry for the typo, will not say or overstate their answers. So to avoid all those kinds of response errors, we ensure that there are possible checks and skips in the questionnaires that we adopt. Now, these are some of the kinds of sampling that are available. So, on the left hand side, you would see probability sampling. On the right hand side, you could see non-probability sampling. There are some examples of probability sampling mentioned on the left hand side. There are some examples of non-probability sampling mentioned on the right hand side. If you can see the first one, simple random sampling. We've been talking about random sampling since yesterday. So this is the one, this is the culprit that we've been talking about. And this person is basically responsible to ensure that there is no bias in our sample. So this is the best kind of sampling that you can adopt, simple random sampling. Simple random sampling requires 2 to 3 things. So for example, in this classroom, if I would do a simple random sampling, say out of 20 people, I need to sample 5 people. First requirement is that I need to have the list of all the 20 members. If I have the list of all the 20 members, then I'll generate random numbers for 5 people. I'll simply select 5 members there. Okay. So that is simple random sampling. No bias is included. The kind of findings that you can present out of your study will be easily acceptable by anyone. Systematic random sampling. What is a systematic random sampling? Systematic random sampling. Okay, so if you see, I have also shared a YouTube link here. So wherever you get these presentations, please feel free to go through the YouTube link also. That will be really very helpful. So for systematic random sampling, first of all, let's talk about simple random sampling, SRS. Simple random sampling, 20 list of 20 people, randomly sample 5 and interview them. Simple. Now systematic random sampling, let's say you were supposed to sample 5 out of 20. Okay, and you have the list of these 20 people, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. So for systematic random sampling, we need to get 2 things in place. One is a random start. The other is a sampling interval. These 2 things. For systematic random sampling, we need these 2 things: random start and sampling interval. What is a random start? Between 1 to 20, if I go to Excel, if I simply generate a random number between 1 to 20, it will throw a result. Okay, let's say the first number is 17. Okay, so let's say the first number is 14. That is the random number that you've chosen between 1 to 20. So Excel has given you a random number between 1 to 20, which is 14. Okay, so this becomes a random start. Alright, we have 20 is a total number, right? We need to sample 5. Okay, so it is simple, 20 by 5. 4 is your sampling interval. What do we need to do? So 14 was the first sample because it was a random start. Keep on adding 4 to it. 1, 2, 3, 4. This is the second sample. 1, 2, 3, 4. This is your third sample. 1, 2, 3, 4. This is your fourth sample. 1, 2, 3, 4. Fifth. So the respondent on these positions are basically the ones that you need to interview. What is the difference between a simple random sampling and a systematic random sampling? Besides the calculation, in systematic random sampling, you could have simply randomly chosen 5 people out of those 20 and gone ahead with the survey. In this kind of a situation, you have created the list first, you have selected the random start first, started adding those sampling intervals to come up with your 5 samples. Why do we use this and not SRS in certain kinds of situations, or in which kind of situations would you use a systematic random sampling over a simple random sampling? Okay, simple. So in Excel also happens at times that if you simply generate a random numbers, 5 random numbers between 1 to 20, there's a possibility you might get numbers like these: 1, 3, 4, 5, 17. Okay. Now think of the situation of a village. If you were to conduct a study in a village which has around 200 households, right? And you have the list of 1 to 200 households, right? And you were supposed to get a simple random sampling out of it. And these are the numbers that you get: 1, 3, 4, 5, 17. Which means, though these are random numbers, but still they are concentrated in one small portion of the village only. Which means that my sample might not be a true representation of the entire village, of the entire population. Right? So in certain kinds of situations, SRS can be difficult. Though this rarely happens, but this can also happen at times. Right? So we go ahead with a systematic sampling in these kinds of situations. Okay, so in these kinds of situations, no matter how large the sample is or how large the sampling frame is, you will still get samples from different points across the village, different points across the population, right? So this is another way. So we've talked about simple random sampling, we've talked about systematic random sampling. Okay. Random start and sampling interval, right? The third is stratified random sampling. What do we do in stratified random sampling? We would have heard about this, no? Stratified random sampling? Never? Okay. So, remember cohort that we were talking about? So, cohort is a set of people who share some similar characteristics. So, strata is also strata. So, stratified is basically coming from strata. So, we are talking about people who share some similar characteristics. So, we are dividing our sample into such kinds of people. Okay. For example, let's say in this group, I want to do a study which basically talks about what is the difference in the education status of the males and the females in this class. Right? So there are two strata here: males and females. Right? So in my sampling process, what will I do? Let's say there are 20 members in this 20 participants here, right? Out of which, let's say there are 12 females and there are 8 males, right? Now I have two options. Either I do a simple random sampling from these 12, right? Or I do a systematic random sampling. Similarly here, SRS or a systematic random sampling, right? What is the difference here? The only difference being that I am trying to get two strata differentiated in the first place. So this is stratified random sampling. Okay, we did not have strata in systematic random sampling or simple random sampling. Okay, why do we do this? Why did we differentiate it between males and females? Because the objective of the research that we are trying to conduct is to understand what is the difference between the education status of the males and females. Now, if the objective was supposed to understand what is the difference in the education status of the people who are from northern Meghalaya and southern parts of Meghalaya, right? So I would have created two separate strata: northern Meghalaya, southern Meghalaya, right? This could have been like 14 people coming from here, 6 people coming from here, and then again I would have used SRS or systematic random sampling. Similarly, SRS and systematic random sampling. See, so it is, the strata is also coming based on either your intelligence. By intelligence I mean, so for example, if you're talking about in terms of an income study, right? You would want to understand what are the different kinds of covariates that also affect your household income. So people who have been a part of the program, people who have not been a part of the program, right? So that would be a kind of intelligence that you would use from your end based on your understanding of the program, right? In this case, it is very simple. The question is asking what's the difference between the education status of the participants who are from North Meghalaya vis-a-vis Southern Meghalaya, right? So that's why the strata has been created. So strata is also fine. Okay. Last is the cluster sampling. What is cluster sampling? So you can see the definition of cluster sample here. It states a probability sample in which each sampling unit is a collection of elements. Okay. When is cluster sampling used is also mentioned there. Can we just look into those 2 points? It says a good sampling frame is not available or costly, while a frame listing clusters is easily obtained. The cost of obtaining observations increases as the distance separating the elements increases. A sample of 1,000 households is divided into 20 clusters with 50 respondents sampled in each cluster. So this is maybe too simplified a language, right? Sometimes that is also difficult to understand. So I'll keep it very, very simple. What is happening right now is that we were talking about a sample of 20. Let's say we were talking about a sample of 100. So all of this was easily manageable. You could have done a simple random sampling. You could have done a systematic random sampling. You could have done a stratified random sampling, stratified sampling, sorry. The fourth one is cluster sampling, and this is the sampling that we end up doing almost all the time. Okay, so let's say you are trying to understand proportion of children enrolled in school in Meghalaya. Percentage of children enrolled in schools in the state of Meghalaya. That is what you're trying to understand. That is your research question. Okay. Now, state of Meghalaya is so large, right? How do we go about sampling? Do we have the list of all the children in the state of Meghalaya? Probably not. Which it said, a good sampling frame is not available. Right? That's what we were talking about. The sampling frame is not available, which means that list of 1 to 20, that list of 1 to 100, that is not available. What do you do in that kind of a situation? Which will happen most of the times in the kind of studies that we undertake, in the kind of projects that you are working on. It will happen most of the times. You won't have the list of all the people, which means you don't have a sampling frame. Right? What do we do in this kind of a situation? The state of Meghalaya has 12 districts. To ensure that you have a sample that is representative of the entire state of Meghalaya, you would want to include some sample from each of the districts. Right? Are these districts your clusters? So each of these districts will have their own characteristics, right? So that's how it becomes a cluster. Right? So 12 districts, but then do we have the sample? Do we have the list of students in each of these districts? No, we don't. Right? Do we have the time and money to actually go to all the children? Or if, let's say, 12 districts is what I've selected. Can I do a simple random sampling just to select the children from each of these districts? I can do that, but it's going to be massive. It's going to be massive resource intensive. Let's say in one district there are 10,000 children who are in the age group of 5 to 18 years, the school going age, right? In one district only. And if I simply do a simple random sampling, let's say even if I had the list of those 10,000 children, if I do a simple random sampling, one of the children might be 2,000, the other child might be 3,500, the other child might be 4,700, 6,900, 9,900, and so on and so forth. This child might be present in some block in some village. This child might be present in some block in some village, so on and so forth. That is not a good utilization of my time and resource, right? Of anyone's time and resource. So what do? We adopt a clustering approach. And we try and minimize all these hassles. So in each of these districts, I'll say, let's go to how many blocks? Let's say 2 blocks each. 2 blocks each. That makes a total of 24 blocks. Right? Now let's say, can we go to all the villages in these 24 blocks? I mean, we can, but we need a lot more resources. Why spend so many resources? Right? We can go to, say, 10 villages in each block. That is also a lot. Let's go to only 5 villages. Okay. 5 villages. So that would mean 120 villages. Right? Got it? And within each of these villages, Let's sample 10 students or 10 households just to check if all the children in those households who are in the age bracket of 5 to 18 years are they enrolled in the school or not, right? So let's look at 10 households from each village. That makes a total of 1200 households. Now this is a much more cost effective way of going ahead with the sampling. 1200 households in which I have very clearly figured out that these are 12 districts, 2 blocks from each, 5 villages from each of these blocks, 10 households from each of the villages that have been sampled. I know which blocks to go to, I know which villages to go to, I know which households to go to. Or maybe if I don't know the households to go to, I can simply do a simple random sampling or a systematic sampling here, right? Now, do you have a question here? Please ask me a question here because there is something that I have not explained here. Let's say if I have to select 10 households from each of these villages, do I have the list? Do I have the list of all the households in that particular village? In most situations, I won't have the list. Even if I can do a complete listing exercise, but it's going to go very, it's going to have a dent in my pocket, right? So what do I do? There are different ways. So for example, the ideal way would have been that I go to each of these villages, get the basic identifiers from all the households that are there in the village, for which I might have to visit like 120 households. What is the usual household population in the state of Meghalaya? It might be somewhere close to 100, 120, I guess, or 80 households per village, something of that sort. Right. So anyway, let's peg it at 100 villages. Okay. So I would have to go to 100 households and then collect the basic information and then prepare a list and then go ahead with a simple random sampling or a stratified or a systematic random sampling. Right, that is one way, that is the most ideal way, but obviously that takes more resources. What do we do next is that we sit with any village head or any person who has a good knowledge about the village boundaries, right, and we prepare a social map with them. What is a social map? A social map is a very crude form which basically outlines the boundaries of the village, right? So for example, if you sit with a village headman or a person who has a very good understanding of the village, right, about the different kinds of resources, the number of households in that village, what you do is you will just simply sit with him or her and then you will identify the north direction there. First of all, identify the north direction there, then try and understand what are the boundaries like of that village. Let him draw the social map for you, right? Then he would say, or that the lady would say that yes, we have a school here, right? So a school could be mentioned like whatever. I mean, you just mentioned an S here, right? Then you might say that there is a sub center somewhere, right? So here is a sub center, and you mentioned, right? Then you would say that person might say that there is a church somewhere, right? So you mention a church somewhere, right? So the other person might say, okay, there is a stream that flows somewhere to the middle of the village. So you demarcate the stream here, right? Right. Then someone might say, okay, we have this area is a fallow land. So fallow land. Okay. Some people might say, okay, so now you might start asking how many households are in different parts of the village. Then some people might say, oh, there's a certain tribe that actually, so there are only two tribes in our village. Maybe there are three tribes in our village, they might say. Or there are three caste categories in our village, right? And they might say that this is the entry point of the village. This is one road, which is not exactly a pakka road, but some sort of a semi-pakka road, right? So in this part, tribe one households are there, right? In this part, tribe two households are there. Tribe one, probably the total number of households here are around 250. Sorry, my bad. The total number of households are 60. And here, though we have a larger space, we only have 40 households here. This is for tribe 2. Right. Now you've created a social map here. That's a bad diagram that I've created on the board, but this is how it usually looks. So once you prepared this, what do? You have basically two segments here. There are two areas which can be demarcated using natural or artificial boundaries. So this is one area. This is segment number 2. Segment 1, segment 2. Okay. This segment roughly has around 40 households. This segment roughly has around 60 households. Let's say you have to sample 10 households, which is a good representation of the entire village. What will you do? 10 has to be distributed across these two segments. I do a proportionate sample. I distribute my sample proportionately to the total number of households in each of these segments. Very simple. So in this one, right, what do I do? What do I say? Six households will come from here, right? 4 will come from here. I have distributed this. Very simple, right? How have I done this? 6 households. Can anyone tell me? How have I done this? Anyone? Ten households were supposed to be selected, right? So if I say that 60 is the total number of households in this particular segment, I have to sample how many? 10. Sorry, 10 out of 100 multiplied by 60. That's what I'm talking about. I had to sample 10 households out of a total of 100 households in that particular village. And this particular segment had 60 households. So I multiplied it by 60. Similarly, 10 by 100 multiplied by 44. This is for segment 2, this is for segment 1. Segment 1, segment 2. Simple. Right? So now what do I do? Once I have decided that I need to sample 6 from this, again I don't have the list of the 60 households. Okay. So when I just go here, I probably just stand here at the center. I feel that the sub-center is at the center of the village. Right? The sub-center is at the center of the village, and then I start following the right hand rule. What is the right hand rule? You simply take your right hand, you pull the thumb out, right? Whichever direction it points to. So it might point to this direction, right? The first household that is here, you interview that household. That is your first sample, right? And then you follow a systematic sampling, systematic random sampling. That becomes your first household, and in the right hand side there'll be another household. So there'll be a sampling interval that you keep adding to it. Okay. Every time, say that list of households end, then you move to the other set of households. Open your right hand again with the right thumb, start moving in that direction. So that nth household will be selected. Simple. I've selected this household, then the 6th household might be selected, the 11th household might be selected, the 16th household might be selected, and so on and so forth. Right? Depending upon the sampling interval that you have. Got it? So this was simple, right? Which means an SRS is not possible because you don't have a list. So SRS cannot be done, right? You can't just pick and choose certain households and say that this is random sampling, this is not. Right? For random sampling, you need to have a list of households. You need to have a sampling frame in place. So systematic random sampling comes to a rescue. Okay, so this is fine. This is how cluster sampling is done. You would always find clustering approach being followed, clustering sample being followed in most of the studies that you are doing, because the kinds of programs that we're working on, large scale programs, and their evaluation or research obviously includes a larger geography. So to account for all of that, we definitely need a cluster sample. Now all these 4 points that we've discussed right now, these fall under probability sampling. Why do we call it probability? Probability, chance. The reason why we call it probability sampling is because each of the members or each participants in the sample have an equal opportunity to be selected in the overall sample. Each member in this sampling frame has an equal opportunity to be selected in the overall sample. So there is some mathematics included in this kind of sampling. This is a more scientific way of sampling, right? Whatever findings that emerge out of the study, you can say that I am certain that this finding can be generalized to the entire population, can be inferred to the entire population, right? Now let's say you've not done this, you've done this. Let's say you've done this non-probability sampling. Non-probabilistic sampling. Okay. What is convenience sampling? What is convenience sampling? In this room, if I have to come up with research finding, I think that I get along with the 4 ladies sitting in the first 2 rows, and I'll just collect data from them, and that will be the end of it. So it is a convenience sampling, right? Convenience sampling could also be like whoever comes first, I interview them. That's all. Do the members in this group stand a chance of getting selected in the sample? They don't, right? So convenience sampling is a non-probabilistic sampling, and that's why the findings cannot be generalized to the overall population. Simple. The other is judgment sampling. What is judgment sampling? So judgment sampling is where the researcher bias actually comes into play. According to me as a researcher, I would rather want to interview 2 members from here and 3 members from here. And those 2 members I will identify. Those 3 members from there I will identify. Maybe people who I think would have a good understanding. So I have included my judgment into the sampling process. Again, that is the researcher's bias. And we always wanted our sampling to be free of any kind of bias. So judgment sample. What is quota sample? What is quota sample? Anyone? Sorry? Yeah, to a certain extent. So quota sampling is basically if I want to study this group, I would simply say, okay, let me have a representation from the male members and the female members also. So out of the females, I'll simply draw two respondents for my study, and from the males also I'll draw like two members for my study. And this is mostly going to be a purposive sort of a study. It's not like that all members in the group have the same chances of getting selected. So you have divided just like straight up. We have certain quota for certain people, and then I'll get you to be a participant in my interview. So that's simple. I'll get some representation from the females. I'll get some representation from the male members. But that quota might not be a true representation of the entire population. I might select two members from five female members, right? And I might select two members from a larger male population. Again, it's no random selection here. There is a lot of bias that gets involved here. So quota sampling, again, the findings cannot be generalized to the entire population. Now the last one, what is the snowball sampling? There is another kind of sampling that we usually use, and snowball sampling is used in situations. I'll come to that later. So snowball sampling, what happens is that, say I am dealing in a kind of research that has a social taboo to it. Okay. For example, let's say people who are suffering from tuberculosis. The tuberculosis usually has a social stigma attached to it. People think that one should stay away from these kinds of people in the let's assume for example, let's say one of the patients that I approach has tuberculosis. I know someone who already has tuberculosis, right? So I approached that person, conducted the interview, and probably because he goes to the dot center regularly, he knows a few other people who have tuberculosis and they're getting treated right now. So what he'll do is, I'll just check with him. Can you also tell me or put me in touch with a few other people? I want to conduct a study. So that person might give me leads to three other people who have tuberculosis. I go to those three people, conduct the interviews with them. Those three people might give me some reference to six other people. I go and conduct the interviews with them as well. So it's basically I'm just rolling the snow. So that's why snowball sampling, right? I keep on adding more numbers to my sampling frame, to my sample as I move along. Again, I have no clue about what the sampling frame is. So obviously, I cannot be certain whether the findings that emerge from my study, whether they are true for the entire population or not. Okay, so that is snowball sampling. So these are non-probability samplings. Now, is non-probability sampling better or worse than probability sampling? Obviously, it is not non-probability sampling, but there are situations where you don't have a sampling frame at all. You can't generate a sampling frame at all. In those kinds of situations, you have to live with what you have. Right, so you will have to go ahead with non-probability sampling in those kinds of situations. Great. So that was all about sampling. Now there are simple two formulas. And before going to formulas, so it is already 4 o'clock. I'll just try and wrap it up as soon as possible. Okay, so first is null hypothesis. Pessimistic people, as we are, we start with saying that there has been no difference, no change, right? The alternate hypothesis is what we are trying to test. We are basically trying to test the null hypothesis, and alternate hypothesis says that there is a difference between certain characteristics of the population. What is significance level set at 5%? So there is a p-value for each indicator that you come up with. So for example, I'll just run a stata code for you. So this is one of the data sets that I have that is already available in Stata. I'll just put that in front of you. So this is the data for certain cars that have been manufactured. This is the list of the cars. These are their prices in USD. These are some of the other characteristics of the car. I'm not sure about what MPG is mileage. MPG is mileage. If you can see here, MPG means mileage. Then Rep 72 means repair record 1978. We are basically looking into some record that would have been created by the US department. Then the headroom of the car, the trunk of the car, the weight of the car, the length of the car, the turn of the car, basically the turning radius of the car, displacement of the engine, right? So all of that is mentioned here, and whether it's a foreign make or whatever, right? So that is mentioned here, right? Now, can you just give me a sense of, if I were to run a regression, what could be the dependent variable and what could be the independent variable here? Just play along. I mean, just throw ideas here. Yeah. Price of the car is the dependent variable. Perfect. So dependent variable, price of the car. It can be dependent on. I'm just saying it's directly proportional to. Okay. So if the price of the car will be higher if maybe longer cars might be more expensive. The Chevrolets. If it is a heavier car, it might be more expensive. The car with larger headroom might be more expensive. The car with a larger displacement of the engine might be with a bigger engine, might be more expensive, right? And the car which is of a foreign make is more expensive. So what did we say right now? All the statements that I made these are hypotheses. These are hypotheses that I can test. Okay. So what can I do? I can simply do a regression. Regress price, your dependent variable, and then let's say the other variables that we were talking about, right? So y is price, and then now we are talking about all the independent variables, x1, x2, x3, x4, right? So headroom is one, trunk is other, weight is other, length is other, turn, displacement, gear ratio, and foreign. Okay, I'll just hit an enter here. This is the kind of output that you usually get as a part of any regression model. Okay, Don't get bogged down by the different numbers that are mentioned here. Just focus on a few things. This is a multivariate analysis, right? We've come back to the same point. Y is equal to mx plus c, and then there will be a c somewhere. Okay. So this is m1 x1, m2 x2, m3 x3, m4 x4, mn xn, right? And you can have multiple c's also, plus c1 plus c2 plus c3 plus c4, which you can club together to form a constant, which I've mentioned here, right? That is the scene that basically in mathematical terms, this is what we are trying to do here. Okay. So these are, you can see COEF dot, these are coefficients. These are the slopes. This is M1, M2, M3, M4, M5. What is X1? X1 is headroom. X2 is trunk. X3 is weight. X4 is length. X5 is turn. And so on and so forth. Right? Now this is the significance level that I'm talking about. Don't get bogged down about how many numbers, whether it's a three-digit number here, 10-digit number here, it doesn't mean anything if this value is not less than 0.05. If P simple, I'll just say one sentence only, and please bear with me. Null hypothesis says that there is no change. Alternative hypothesis says that there is a change. The evaluation tests the null hypothesis. Okay? The moment the p-value for any indicator is less than 0.05, it means that the null hypothesis should be rejected. Okay? That is simple, right? One term. If the p-value, it's basically the probability score. If it is less than 0.05 for any particular indicator, the null value is rejected, which means that there is a change. Okay? And this value should be considered only if there is a change here. So let us look here. Which values are less than 0.05? Headroom 0.066. Drop it from the equation. There is no substantial evidence based on the data that we have to say that there is a correlation or there is a strong relationship between headroom and price. Okay, drop it. Trunk 0.520. It is not less than 0.05. The data does not substantiate any relationship between price and trunk. We drop it. Weight 0.000. That's a triple star. So the weight of the car is directly proportional. And why is it directly proportional? So if the weight of the car increases, it is 4.92. Right? So your M3, the third slope, is 4.92. It is a positive number. Right? So what we are trying to say is that the weight increases, the price increases. Okay? So if this is price is equal to 4.92. Yes, 4.92 times weight. This is what we are trying to say, right? Plus There are other factors also, no? 0.077 length drop, 0.177 turn drop, 0.122 displacement drop, 0.914 gear ratio drop, 0.000. Whether it is a foreign make, if it is a foreign make, obviously it is more expensive, right? So you'll have to pay a lot more taxes to get the car into your country, plus 3485 3485 times the make of the car. So this is the equation, which means that weight is a factor which is important, but it is important if you were to compare between weight and make. Obviously, make is a much better contributor to influencing the price of the car. That is what we were simply trying to say. Also, what we are trying to say is that if you increase price by 1 unit, it is 1 here. If nothing is mentioned, it is 1, right? 1 multiplied by price, it is. The price increases by 1 if the weight of the car increases by 4.92 and the make increases by 3485. Right? So that's the equation that you can come up with. Simple. Right? So this is the regression equation. Basically, you try to draw the relationship between price and weight. Now, using this equation, if I am someone who is into car manufacturing and this is the algorithm that I've come up with, I can simply try and understand what should be the weight of my car and what should be the make of my car. Right? If I want to keep the prices low for my car, I would rather want to make it internal. It should not be a foreign car. It's a very simple interpretation, right? It should be an in-house or in the country made car, made in USA, right? And then the weight should also be lesser. If the weight is less, the price will be less. Simple? Okay. Now, so significance level is something that I've already talked about, right? Type 2 error. So there are 2 types of errors. There are 2 types of errors. Type 1 error, type 2 error. Type 1 error is called significance, for which the p-value should be less than 0.05. We peg the significance error or the significance level at 5% only. So this is type 1 error. Now I'll explain this with an example. What is type 1 error? Let's take the example of a COVID vaccine. I am the manufacturer of a COVID vaccine, right? And there are people dying everywhere and every day. And there are millions of people dying every day. So the responsibility on my shoulders is immense, right? And I have to get the vaccine tested and prepared as soon as possible and roll it out into the industry or into the sector so that people's lives are saved. Okay, there are 2 kinds of errors that will creep into the system. Number 1 is that my vaccine did not work actually. It is not effective, but I thought it was effective. Okay, I prepared some version of my. So when we write reports also, there are a lot of drafts, right? Let's say the first draft that I've developed, I took it for testing. I conducted some experiments with it, right? But my findings suggest that it was working. But when I actually rolled it out into the actual world, it wasn't actually working. People were not getting treated of COVID. There was some issue with the experiment that I conducted. Right? So that kind of an error where you think things are working, but in actual it is not, then it is a type 1 error. Okay? There is another kind of error, which is type 2 error, which is called false negative. False negative is when I've developed some version of my vaccine, I've sent it for testing, and after going ahead with the rigorous testing, my test results basically tell me that it's not effective. So I don't roll it out into the world. When in actual practice, it was actually working. So the amount of time that I hold back the vaccine because my test results are saying otherwise, a lot of people are dying every day outside. So type 2 error is obviously a bigger error than type 1 error. Okay. So these are two types of errors, type 1 and type 2 error. So this is alpha, this is 1 minus beta. Sorry, this is beta, and you will always hear me say that the sample size should be powered enough to provide reliable estimates at the population level. What is power? Power is, so type 2 error is usually pegged at 20%. No matter what you do, it should be relaxed a bit so that you are able to roll out your vaccines out in the market. This is usually pegged at 5%. This is the significance level. The corollary to it would be the confidence level. So confidence level is 1 minus significance level. Confidence level is 95%. Okay. Similarly, type 2 error is usually kept at 20%. Right? But this 20% does not mean, 20%, if you remember the kind of efficacy that people were talking about the COVID vaccines, some said it was 87%, some said it was 82%. So Covaxin was said to be more efficient as compared to the Covishield, right? 72% or something of that sort, right? So they're basically talking that out of 100, 20% of the times it might not work, and 20% of the cases it did not work. So we talk about power, which is 1 minus 20%, 80%. So for all social development studies, you would always see that the power is kept at 80%. Okay. Significance level is always at 5%, confidence level is at 95%. Just remember these terms because we are going to about to calculate the sample sizes also right now. Okay, power is pegged at 80% for social development studies. Now, what do we have to lose if we peg this at 20%? Not much for human subjects. So, for example, if I were to say that a project has worked or not, there is a possibility of 20% for type 2 error, that whatever findings that I come up with, maybe the project has worked, but probably I am saying it has not worked. Right? False negative. Right? But that is still fine. It's just an evaluation. Okay? But what if I was supposed to roll out a vaccine? This sample would have been much higher. It should have been 99% or 99.9%. Right? And the significance level should also have been not at 5%, maybe at 1%. So you would always find clinical studies being conducted 99%, 99.9%. Right? So that's the kind of difference between the clinical studies and our social development studies. Okay. Oh, sorry. Yeah, it's 4:20 right now. How about we complete the session in the next 20 minutes and then we break for tea? Okay. Apologies. Uh, okay. So there are very, very simple formulae that you can easily use, and I'll share it with all of you uh, after the session today. Yeah. Okay. Let's quickly close this. Okay. Simple formulae for descriptive research and exploratory research. Please use one sample formula or Cochrane's formula. Smaller samples, Cochrane's finite population correction. For evaluations, two sample there are two formulas that we are going to talk about today. One Cochrane's formula or one sample formula, right? And the other is a two sample formula. Okay, so what happens here? There are few values, as you can see on the screen. This is the formula. This is also called Cochrane's formula, right, which is used to calculate sample sizes for cross-section studies, descriptive studies, exploratory studies. Okay, what do we do in this kind of study? It says n is the sample size, d is the design effect, z score are the z scores going back to 9th standard, 10th standard, 11th standard. They used to be log tables that were provided to us. We used to somehow locate the z score on those tables. Remember those days, difficult days, right? So that is basically the z score. And then P and Q, I'll also talk about what is P and Q. And the one E square at the bottom is basically the sampling error, right? So let's see what a design effect is. Design effects value actually ranges from 1.0. It could be anything after that, right? It could be like 10 also, it could be 12 also. But for all good studies, reliable studies, the design effects value should be from 1.0 to 2 to 3. Maximum, not beyond that. What is a design effect? We're talking about design and its effect on the sample size. if you can also see here, your sample size is directly proportional to the design effect, right? Which means if the design effect goes up, your sample size also goes up, right? And it is inversely proportional to the sampling error. So the lower the sampling error, the higher the sample size would be, right? So if you try to reduce the sampling error, your sample size will shoot up, and by a good margin, because it is inversely proportional to the square of sampling error. But I'll just put that in English right now. Okay. So sampling error, what we talked about earlier, I have to interview 1 crore people. I've conducted one study with 10 lakh people, the other study with 1,000 people. The sampling error is basically the difference that I get if I move away from a population survey. So if I'm moving away from 1 crore sample size to 10 lakhs, I'm losing out on 90 lakhs. That is still okay as compared to moving from 1 crore to 1,000 samples, right? So obviously the sampling error in the 1,000 sample would be much larger as compared to the sampling error in the 10 lakh situation, right? So, I mean, that's completely reflective in the sample size calculation as well. No? The sample size is 10 lakhs in one case, in the other case it is 1,000. Okay, so the more the sampling error, the lesser would be your sample size, and vice versa. Okay, now for calculating the sample size, we need few values. Let us say that what is your research question? If your research question is, I want to understand the literacy level in this group, right here, right now. Okay, the proportion of people who have studied for 18 years, the proportion of people who have studied for 20 years, right? So that becomes my baseline value. Now from where do I get my baseline value? Either there is some secondary literature that talks about it, that this group, another study was conducted say a year ago, they said, oh, very nice, I mean 59% of the people have studied for more than 20 years, right? And if there is no baseline, what do we do? Or if there is no data available in the secondary domain, what do we do? You simply put in 0.5 because 0.5 will give you the maximum sample. And if you have the maximum sample, nobody can question you, right? So if you don't know the baseline estimate of your key outcome indicator or your key research question, simply use a 0.5 because at 0.5, the sample size would be the maximum. Okay? So the value of P is 0.5. Again, the value for Q, which is 1 minus P, is 0.5 because 1 minus 0.5 will be 0.5. Maximum error allowed, you kept it at 5%. So for all social development studies, you would find a 5% sampling error mentioned. 5% error is basically 0.05, 5%, right? And then this is the z-score that is corresponding to a confidence level of 95%. Okay, so instead of looking into the log tables and the z tables anymore, we can simply Google these days. Okay, so just Google it, z-score corresponding to 95% confidence level or z-score corresponding to 5% significance level. You'll get this value 1.96 in the z table, or if you want, you can look into the tables also. Right? Yeah, and let's finally come to what is design effect. What is design effect? The variance in the sample to the variance in the population. In population surveys, there will be no variation. If you've interviewed everyone, you're not missing out on anyone, right? So, variance in the population is 1. Design effect basically shows you how much have you deviated from the simple random sampling. Sorry. if you had gone ahead with a simple random sampling here, and obviously you don't go ahead with a simple random sampling, let's say you have adopted a cluster sampling in your sample, right? So it basically tells you how much have you deviated from a simple random sampling. I'll just tell you in English what that means. Is that, let's say the total sampling frame was of 1,000 people, right? The ideal scenario would have been to interview all these 1,000 people, right? Now let's say I'm not doing that. That's also fine completely. That's not a problem. Let's say I'm using a sample survey, a simple random sample. I have the list of all these 1,000 people. I'm just drawing a sample of say 100 out of these 1,000. But that is a simple random sample. It's completely random. I have the list of 1 to 1,000. I have simply used Excel, and Excel has thrown me 100 numbers. I've gone to these 100 people. They might be in any block, they might be in any district, no matter how much ground I have to cover, but I will cover only those people or interview only those people that have been randomly selected by the software. Right? In that case, the design, there is no variance, there is no deviation from the simple random sampling in our sample. There is no deviation here. So the design effect is 1. For all studies that follow a simple random sampling, the design effect is 1. But in most cases, you don't follow a simple random sampling. So what will happen is the variance, because of using this cluster sampling, will keep on going up. I don't use an SRS anymore. I use a cluster. So what I've done is, in my 5 districts, I've gone to 2 blocks each. Then from each of these 2 blocks, I've gone to 5 villages each. Then from each of those 5 villages, I've gone to 10 households each. Right? I've used a cluster approach. In which case, I am not traversing the entire sampling frame. Right? I'm just looking at a smaller cross section of it. Right? Which means I'm losing out on certain population. I'm deviating from a simple random sampling. So in that case, if you talk about NFHs, the design effect there varies from 1.5 to 1.6 for most indicators. Right? As I mentioned, for all the good studies, it must be somewhere close to this. 1 to 2.3 or 2 or 3 max, not more than that. So this is what it is, right? Now design effect is also calculated using one more formula. 1 plus rho n minus 1. I'm just saying this because it is getting recorded. Probably you can look into the recording later. Okay, so design effect is equal to 1 plus rho. What is rho? This is intra-class correlation. Intra-class, which means within the class there is some correlation. What is correlation? There is a relationship between the kind of responses that you're getting from the same people. So for example, let me assume that people who are working on child protection schemes, they're working together, they have some sort of a similar understanding on certain topics. If I ask you a question, because you're coming from that sort of a mind frame, your responses might have some similarity. Right? If there are certain people who are coming from the planning department or the statistics department, they think in a certain way. If I ask them a question, probably because they come from that mindset, they might give you a certain kind of a response, and there might be similarity in the kinds of responses that they are giving me. So there is some intra-class correlation that is already existing in the kinds of groups, because I'm concerned about clustering here, right? So each of these clusters, there is a similar kind of response that I'll get. If I go to 10 villages in one block, because they are falling under one block, obviously the kind of responses that I might get from those 10 villages might be similar to some extent, right? So that is intra-class correlation. Now, intra-class correlation, the value you get from secondary research. Yeah, right. So the studies that have already been conducted, they would give you a value of anywhere between 0.01, 0.05, 0.06. Sometimes it is 0.1 as well. These are some of the values that you would largely see for intra-class correlation. Now, I'm not sure if you've looked into it, but NFHS usually goes for 22 households in each of the villages that they sample. So this is the total number of households in each of the villages right? So if I go ahead with this, 0.01 multiplied by 22 minus 1, which is 1 plus 0.01 into 21, 1 plus 0.21, which is equal to 1.21. So that becomes the design effect for NFHS, right? Again, this is in the same range that we were talking about, right? Okay, so this is, let's assume this design effect and calculate our sample size. You don't know the baseline value. Sorry. Right. Let's assume you don't know the baseline value of your key research question or key indicator. So let's peg it at 0.5. Your Q value also becomes 1 minus 0.5, 0.5. Maximum error is at 5%, 0.05. This is the z-score corresponding to a confidence level of 95% or a significance level of 5%. For a simple random sampling, this is the number that you will get. This is the minimum sample that is required. 384, this is the magical figure. Please always remember this number. For any exploratory study, if I were to present some estimates at India level, at the national level, this is the kind of sample that I need, 384. Right? Now you would think, why do the agencies quote so much if they have to simply just get a sample of 384? Right? Sometimes these guys say that 6,000 sample is required, 10,000 sample is required. Because to conduct this survey, you need to have a simple random sample in place. And for a simple random sample, you need to have the list of all the members or all the members in the sampling frame, which is the entire country, at your disposal. And then you will simply go ahead with selecting 284 respondents from there. And these 384 respondents would be in any state, in any district, in any block, right? In any village. So you might have to travel a long way to actually come up with this estimate. Okay. Now obviously this is an ideal scenario. Nobody does that, right? So we will follow a clustering approach, which means a design effect goes up, right? The moment you increase the design effect to 1.21, NFHS 1, or a safer way is to simply pick it at 1.5. You see the sample size has gone to 576, right? It has increased, right? Now just try and look at what we are trying to do here. If I am providing national level estimates, what I'll be doing, I'll be dividing the country into five or six zones. Could be north, south, east, west, central, northeast, right? 6 zones. Then what I'll do is I'll look into the number of states that come into each of them. I'll select one state from each of them, which means 6 states. 6 states, I'm looking at 5 districts from each of these, right? 6, 5, 30 districts. 30 districts, let's say 4 blocks, 5 blocks from each of them. 150 blocks, 150 blocks, say 10 villages from each of them. 1500 villages. 1500 villages, then you're talking about say 10 households. 15,000 is the total sample size, right? It will get difficult to provide estimates using 576 because again 576 usually will not be possible. The design effect will be much higher for if you are going to provide national level estimates. Okay. So this figure will keep on revising. Also, if you see that if you would want to minimize the sampling error, because either you have a sense of what this design effect is from some secondary literature, or you simply keep this at a minimum of 0.01. You get closer to the population if you reduce the sampling error, right? So if I reduce the sampling error to 0.04 instead of 0.05, it shoots up. If I further increase this, also reduce this to 0.03, goes up. 0.02 goes up, and 0.01, right? So this is what we were talking about, 15,000 something. It's coming to 14,000, right? So probably this sample if you go ahead with this sample, you might be a bit more confident in providing estimates on this at the national level for any kind of research that you are trying to undertake. That does not mean that this sample or these samples you cannot defend. Okay. Statistically, you can defend these samples also. Any sample that is more than 384 or 576 in this case, because you are deviating from a simple random sample, so the design effect goes up. Anything more than 570 is something that you can defend. But always keep that 384 figure in mind, because that is for a simple random sample. Okay, now this was about households, this was about individuals, right? Let's say you are not dealing with individuals or households, you're dealing with schools, you're dealing with hospitals, you're dealing with institutions, right? Your intervention is at a cluster level, your intervention is at an institutional level, right? What do we do in that kind of a situation? See, if I'm working with 100 schools, I cannot interview 576 schools, right? Can I? My population is 100 schools. I cannot interview 576 schools, right? So there is a finite population correction, because the finite simply means that, finite as the name suggests, finite population correction can also be included here, which is basically this. So if you mention the sampling universe to be 100, just search for Cochrane's finite population correction. You would find this figure. This is what we are doing here. They've kept design effect to be 1. Okay. And then there is this sample size correction formula. This is the one. This is what we need to do. Okay. So the formula is this. If this was the sample size that you get, right? And if there are only 100 schools that you are working with, so this will be equal to 576 divided by 1 plus 576 n naught minus 1 divided by 577. Sorry. Yes, divided by the total population that is mentioned here. So let's say the total population is 100 households. Okay. So out of 100 schools, you will have to interview 85 schools, if that be the situation, right? But in the case of schools, you can simply go ahead with a simple random sampling. You have the list of 100 schools, right? So in that case, you don't have to go ahead with such a large design effect. You'll have to go with a one design effect. So instead of going to 384 schools, which is definitely not your population also, so you'll have to visit 80 schools out of 100. That is a finite population correction, right? So you go ahead with this sample and provide the estimates. So this is good for descriptive and exploratory studies, right? It is not good for causal studies, because we haven't talked about change at all, right? Let's talk about causal studies. 4:45 now. Let's try and close this in the next 5-10 minutes. There is another formula called the two-sample formula, right? So in most evaluations that we conduct, we end up having a design effect of 1.5, 1.21, 1.62, maybe whatever, right? The larger the number of layers, so if you have a state state disaggregation, district disaggregation, block level disaggregation, the number of layers if you increase, obviously the design effect is going to go up, right? So 1.5, let's take it that value. Let's say the baseline estimate you've looked into certain certain literature, it comes to around 0.5, right? And this is the proportion that you would want to achieve. So how many percentage points are we talking about here? This is the proportion, the baseline, this is the proportion at the end line. Okay, so 0.25 to 0.4, we are basically talking about change of 15 percentage points. 0.15 is the difference, right? We're talking about 15 percentage points, change of 15% points. Say for any indicator, if you would want to measure the sample size with a 15 percentage points, where the baseline value is 0.25, the end line value is 0.4, the z-score for at 5% significance is 1.96. This is the power. That's where an additional parameter comes into play. Power, it's something that we talked about. Power is 1 minus beta. It's the type 2 error, 1 minus type 2 error, which was supposed to be pegged at 20%. So power becomes 80%, right? So this is the z-score. Again, look into the z tables. The value is 0.84. If you would want to increase it a bit to 90%, this value will become 1.645. Okay, and you simply put these numbers here. This is the sample size that you require, 227.5. It's a very, very small sample size, right? But let's say if you would want to detect a smaller change, okay? Let's say you would want to detect a 10 percentage point change from 2.25 to 0.35, right? The sample size has gone up, right? Let's say you would want to detect an even smaller change, a 5% change, 1874, right? Let's say you would want to increase the power from 80% to 90%. So the z-score value increases from 1.645, sample size is increased to 3104. Now this is for treatment, this is for experimental designs, which means the way it should be interpreted is that 3104 should be the sample in, 3104 should be the sample in treatment areas and 3104 should be the sample in the control areas, which means we're talking about a total sample of 6208. Are we done here? No. Okay. So let's say you've undertaken an RCT, right? Then it's okay. Then you go ahead with this. But still, when you go to 62008 households, does it mean that all the households will respond to you? There will be a lot of non-response also, right? So just factor for a 5% or a 10% non-response rate. 6828, the sample size increases, right? Okay. Now, if you remember, we talked about PSM, propensity score matching, when we are doing a DID. And the sample, what happens to the sample when we use PSM? The sample drops. You remember, we match certain people and there would be always certain people that will not be matched to anyone. So that sample will drop from both the treatment and the control areas. So and the drop is largely more in the comparison areas, right? So literature suggests that at least use a 20% oversample in the treatment areas and use a 40% oversample in the control areas. This is the total sample that you're looking at. Add another 10% for non-response rate. The sample increases to 8877. Okay. Now this is a good enough sample size to actually conduct your evaluation. Simple, right? Let's again assume that you were not doing a household survey, you were not doing an individual survey, you were doing an institutional survey. What do we do? Simply divided by the finite population correction factor, right? Which was n multiplied by, I'll just write it here. Probably Excel might not be a good place to write it. This should go into denominator. Sorry, just a second. 1 plus this is the finite population correction factor. Okay, so if you do this, it will be n plus n minus 1 by capital N. This is basically what goes into the denominator, right? What we did for the previous sample size calculation. This will give you a smaller value. If you are going ahead with 100 schools, it will give you some 80 schools, 70 schools, 60 schools, whatever, right? So what have we learned today? We have learned a lot, right? So we started off with a recap of this session. We talked about evaluation designs. Then we further moved into evaluation designs today. We discussed about experimental designs, RCTs, the step-based designs, the pipeline designs. Then we moved into quasi-experimental designs, when the randomness is not possible, or when you think that your sample is not homogeneous at all. In that case, you move to a quasi-experimental design. Quasi-experimental design, there are 4 kinds of designs that we talked about. We talked about double difference design, difference and difference. We talked about PSM, propensity score matching. We talked about regression discontinuity design, RDD design. Then we talked about IV. We talked about instrumental variable or randomized promotion, right? We talked about what are the challenges, how do we go about conducting these kinds of designs in different scenarios, right? And then we also undertook a lot of case studies, right? We found solutions to them. Then we moved to lunch. Then after lunch, we moved into sampling. We discussed about probabilistic sampling. We discussed about non-probabilistic sampling. Probabilistic sampling, what did it include? It included 4 different kinds of samplings. Number 1 was a simple random sampling, followed by a systematic random sampling, then a stratified sampling, and then a cluster sampling. So simple random sampling, you have the list, just draw a random sample. Systematic sample, you have a sampling interval and random start. You keep on adding the sampling interval to the random start, you get a good representative sample. Stratified sample, you get information from different kinds of data. How do you define this data? You define this data based on the research question that you are asking, or your basic intelligence on how you're going to decipher your results. Finally, if you don't have access to the sampling tray, you use a cluster sampling, and cluster sampling is what we will be using in all our approaches, right? Once that is done, we also analyze on how do we go about calculating the sample sizes. So for exploratory studies and descriptive studies, we have to use a one sample formula, which is also called a Cochrane's formula. Cochrane's formula is d z square p into q divided by e square. You don't have to learn it by heart. That is already there in the Excel that I'll share with you, where e was the sampling error, right? D was the design effect. Design effect is the variation. If you are going ahead, variation in your sample divided by the variation that would have been possible in a systematic random sample. So it basically tells you how much are you deviating from a simple random sample, right? The values could be between 1 to 2 to 3, right? You can always safely keep it at 1.5. Okay, sampling error was at 5%. Significance level was at 5%. We talked about type 1 error, type 2 error, which was a more difficult error, which is more of a dangerous error. Type 2 error, right? And we calculated these sample sizes. We also understood why the evaluation agencies look for a larger sample size, right? And for 2 samples, formula. Two sample formula is used for evaluations. You are looking at a change there. So we calculated the sample sizes for 15% change, 10% change, 5% change in the key outcome indicators. If you have the baseline values, well and good. If you don't have the baseline values, just keep it at 0.5, right? And that should be all. Great. So we've covered a lot of ground in these 2 days. It's maybe too much to assimilate in 2 days. And I'm not saying that everyone will become an expert. Nobody becomes an expert. I've been struggling with this for the last 10 years, right? But it's good that we gave it a chance, and I hope that we are more aware, and we tend to use the concepts that we've learned in these 2 days in the kinds of studies that we undertake in future, or at least we are able to guide the other agencies or the other consultants that we work with on different kinds of evaluations and research. I also promise that I will share my phone number and the contact and the email ID at the end of the session. Please feel free to contact me or reach out to me if you would want to discuss anything on evaluation designs, sample size calculations. If you're stuck anywhere, please feel free to reach out to me. My email ID is abhishek.sharma@sambodhi.co.in. My contact number is 9717370733. So I look forward to staying in touch with you guys, and I hope you feel the same about me. Right. Thank you so much for being so patient the last 2 days. Thank you so much. I know it would have been very, very difficult, but thank you so much. The kind of participation that you showed in the last 2 days has been really helpful for me and encouraging for me. I understood the first session probably today was a bit too technical, but that's how it was supposed to be. So, yeah. But thanks a lot. No, thank you. Thank you.